Let's consider a beam spanning span A to B. We are about to calculate the maximum deflection of this beam and equally calculate the slope at 0.7 meter from support A. This is support A. Now, before we go into this, a brief introduction of the Macaulay's method. The Macaulay's method is quite a very simple method. But I must say, before you go into this method, you must have a foreknowledge of how to calculate uh, the moment expression of a beam. So make sure you understand calculating moment expression of a beam so that it becomes easy to take up the expression. All right. So the Macaulay's method has a function, a standard function of x minus a raised to the power n equal to what? 0. The idea is that this function x minus a raised to the power n is equal to 0 when x is lesser than a. All right. Remember that our x is a variable, a is the constant, where s represents distances along the beam. This function is equal to x minus a raised to the power n when x is greater than a or equal to a. Of course, we know that our n could be raised to the power 1, raised to the power 2, and as it goes, it could be any power as the function demands. Now, the idea is, how do we arrive at this? Now, the shear force expression from the beam, elastic beam theory, we know that we have the shear force expression as the flexorial rigidity, which is the differential of our y, where y represents our deflection of the beam. Okay, so you can see the derivative is raised to the power 3. Now, the second derivative on this one, you can see the derivative here is raised to the power 2. When you integrate this, when you integrate the shear force expression, we know that we'll have the moment expression. And we integrate this, we'll have this as EI raised to dy dx raised to power x, which means being differentiated 2 times. Now, when you look at this other side of it, when you integrate this, let's call this function, when you integrate it, let's call it m prime. When you integrate m, you have m prime, which is a function of s. Now, this m prime, when you integrate this other part of it, you are going to have ei dy dx. Of course, we know that dy dx represents slope, meaning this is our slope. So this integral gives us what? The slope expression of the beam. Now, the last one is when you integrate the slope expression, when you look at the deflection expression, you see that the deflection expression haven't been integrated. You have that a function of x, where y represents the deflection of the beam at any point x. Okay, so now let's look at an example of the Macaulay's method. All right, now we have this simply supported beam. This is one of the problems we treated in one of our videos. Please do well to study that video on this particular beam, how to calculate the maximum moment of this beam. We were able to draw the shear force diagram of the beam, and we drew the bending moment diagram of this particular beam. Now let's take a look at this same beam and let's calculate the maximum deflection of this beam, and let's equally calculate the slope at 0.7 meter from the support A. This is support A. Okay, now for us to calculate that, we can as well decide to calculate the deflection at any point along the beam. You can calculate deflection at 0.4 meter away from the beam. You can calculate deflection at the total span of this 18.5. All right, so you can decide to calculate deflection at any point along the beam. Okay, so but for now, let's calculate the deflection, the overall maximum deflection of this beam when all these loads are being applied. And secondly, we also find that, let's see if we can obtain the slope at 7 meter, which is this point, away from this support. Let's get the value of that slope. All right, so quickly, like we said, let's go over and do that. Now the solution, the first thing we are going to do is to obtain the reactions. All right. We'll obtain the reactions like we did in a previous video. We may not be doing that. So quickly, we'll write the value for the reaction. So we know that from the previous video, we know that RA, reaction A, we have the value for reaction A. Is for us to take the moment expression. Now, in Macaulay's method, when you are taking the moment expression is taken for the last load zone. Okay, for those of us who are just watching, you don't have understanding of how to take moment expression, please do wait to visit the video of we did on this particular beam, so you can know how to pick moment expression. Moment expression are taken from load zone to load zone. Now let's look at the various load zone. Like for those of us who are just coming, we have load zone 1, we have load zone 2. From 0 to 4 meter, this is a load zone. From 4 meter to 7 meter, which is here, is a load zone. From 7 meter to 11.5 meter is a load zone. From 11.5 meter to 13.5 meter is a load zone. From 13.5 meter to 15.5 meter is a load zone. So all these are so we have various load zones. Now, among these load zones, this is the last of the load zones, okay? So if this is the last load zone, we are going to cut a section across the last load zone. Please, let's go over and say this becomes our moment. All right. Yes, 20 kilonewton. All right. Yes, 4 meters. Remember, here is 47.54 kilonewton. Okay. Here we have, let's call the section 1, 1. Okay. In this case, like we did when we are taking bending moment and shear force expression, we are not going to take shear force. We're not going to show the shear force because we are much more interested in bending moment. So I'm not going to take the shear force. All right. Now this is what we're going to have. Okay. Now the value for X here, the value for X is at this point. Our value for X from there to the section. So the X is from that point to where the section is being cut. All right. Now, there is something we must understand when we are dealing with Macaulay's method. Now, when you have a turning moment, all right, when you have a turning moment, you are going to take the moment expression in terms of S also, but you are going to assign it to be raised to power 0. All right. So what do I mean by that? Don't worry, I'll do that and you are going to see it. Now let's look at this other side of it. We have a UDL of 15 kilonewton. Unlike what we did when we are looking for the moment expression, we wanted to get the moment expression in our previous class. What you do in Macaulay's method is quite different. When you have a UDL of this nature that didn't run down to the end of the beam, you might have some little challenges. So you are not expected to take your moment expression the way you do it when you are dealing with bending moment and shear force. So it is expected in Macaulay's method, what we do when your UDL is not spanning up to the end of where your moment is going to. So we are going to add a fictitious UDL. All right, that is a fictitious UDL. Okay, so the whole UDL now is as of 15 kilonewton. Now, for us to balance this so that it becomes the original beam, we're going to apply another UDL below it. So I'm going to apply another UDL below it. All right. so that by the time the forces acting upward comes and meets this one, they will strike at each other and go back to the original beam load configuration. So that is the idea we are going to use. So since we have this, we have already taken that, we are going to do that. So all we just have to do is, all we have to do is to add to where we cut the section, and also we're going to add under. Now the UDL you are adding will be of the same magnitude as the UDL, 15 kilonewton per meter. So here will be also 15 kilonewton per meter. Here will be 15 kilonewton per meter. Okay, so that is one. Now apart from that, your couple, by the time we begin to take couple, you assume that this is a load. If it's a point load, you are going to assume it as a point load. And if you assume it as a point load, of course, like we normally do when we are taking moment expression, we will not have the moment expression as this. We'll say that m of x will now be equal to the support reaction 47.54 x. 47.54 times the span will be 47x. All right. Now let's take another moment again. Now let's deal with this turning moment. Now this is an anti-clockwise moment, meaning it's going to be negative. So if it's negative, I said we assume it to be a point load of 20 kilonewton. Okay. When in reality it is a moment. So say 20 kilonewton, then the distance from this point where it acts to section 1, if we want to do it in terms of s, it will be x minus what? The distance from here to here, which is s minus 4. All right? It will be s minus 4. Okay? So that's what we're going to have. So if we do that, we'll now have it as 20 bracket x minus 4 raised to power what? 0. When we see this to power 0, of course, it will cancel, it become 1, and it goes back to 20 kilonewton meter as moment. All right? Now, let's pick this point load. The point load is 30. So when we pick the point load as 30, the next thing we're going to find out is that it becomes what? 30. It becomes 30 bracket. The distance from here to this point is 7. So it becomes x minus 7. Okay? Now let's take the UDL. Remember, we've already worked on the UDL. We've added another one here. So it will now be minus this distance. Now, from here to this point is 7. So it becomes our UDL, which is minus 15 bracket x minus what? 7. The whole of this one becomes x minus 7. That is a load. Load times square over 2. All right. So the whole of this load now will be acting on this distance. And of course, this distance, like we know, this distance becomes x minus 7. So when 15 times it becomes load times x minus 7 over 2, which is the center. It acts at the center of gravity of this point over 2. So if you multiply this out, you will have 15 bracket s squared minus 2. So this is what we have. Now we have this. Now the bottom UDL which we apply to balance it up will be, this one is negative. Of course, we know that the other one becomes positive. So we'll have 15. All right. 15. If we do it 15, what do we have? It becomes 15 minus what? 4.5. It becomes 15 bracket x minus 11.5. Okay, 11.5. The distance becomes 11.5 squared over what? Over 2. All right. Then we have this 20 kilonewton point load. it becomes the distance from here to this point is what? If the whole of this is s, it becomes x minus, where is it acting? It becomes 15 because 13.5. So it becomes minus 20 brackets s minus 13.5. Okay. So that is a moment expression for this last zone. So from this, we can begin to integrate our function. All right. So let's continue with it. We'll have this as m of x equal to 47.54x minus 20 bracket x minus 4 is power 0 minus 30 x minus 7. Okay. We have minus 15 bracket x minus 7 square over 2 plus 15 bracket x minus 11.5 square all over 2. All right. So these are the moment. The last one, which is 20. So minus 20 x minus 13.5. All right. So this is the moment expression. So have we gotten the moment expression? The next thing is to integrate. So we'll do our first integration. We'll have this. Square over 2 minus 20 bracket x minus 4. Then become minus 15 bracket x minus 7. All right, so this becomes minus 15 x minus 7 raised to power 2 raised to power 3 divided by 6 plus 15 x minus 11.5 raised to power 3 divided by 6. All right, so this is what we have. Then now we're going to have minus 10 bracket x minus 13.5 raised to power 2, and we add a constant plus c1. Now the deflection expression, we're having it as this 41.54 raised to power 3 over 6 plus minus 20 x minus 4 raised to power 2 over 2 minus 15 x raised to x minus 7 raised to power 3 over 6 over 3, sorry. I will have it as this. Then we'll have the last expression minus, let's bring in the other one. We'll have 15 bracket x minus 7 raised to the power 4 over 24 plus 15 over 24 x minus 11 raised to the power 4, then minus 10 x minus 13.5 raised to the power 3 over 3 plus first integration c1x plus c2. Now taking boundary conditions at x is equal to 0, our deflection is 0 at the support. So at x is equal to 0, our deflection is 0 at the support A. Now we're going to look at what we're going to have. We'll look for our constant c2. Of course, if we substitute s is equal to 0 into the expression, we are going to have our constant c2 to be 0. So when x is 0, our EY is 0, so substitute 0 all around, we are still going to have 0. So we have that c, we cancel, because we're going to have negative s minus 4 negative. Once you have a negative value, you assume it to be 0 in Macaulay's method. So therefore, c2 is equal to 0. All right, so we've gotten the first constant c2. So we're going to take x is equal to the second support. Our support is 15.5
meters. So at the support end, S is equals to 15.5. At deflection is 0 at support B. Okay, so at support B, S is 15.5 meter, while deflection at that support B is 0. So we substitute it into the expression. We're going to have X, we're going to have it when X is, deflection is 0, so substitute deflection as 0, then substitute 15.53 into the deflection expression. Once we are able to do that into the deflection expression, we can now have our constant C1. All right, we've already known C2 to be 0, so we need constant C1. So let's obtain our constant of integration C1. All right.
That's 10 over 3, 10 over 3 bracket. So solving this, we're going to have 1418.288 as our constant C1. Now let's move over to obtaining the deflection expression. I haven't gotten our constant C1. Let's rewrite the deflection expression. X. All right, so this becomes a final expression for our deflection. Now, I haven't gotten rewriting our slope expression. This is what we're going to have. We have the slope expression as this. Let's rewrite the slope expression. We have 47.515 bracket x minus 11.5 raised to power 3 over 6. We have minus 10 bracket x minus 13.5 raised to power 2 plus our C1. Now C1 minus 141828889. So this becomes the value for the slope expression. So with this, we have gotten the value for the slope expression. So from now, we can now get the deflection, the maximum deflection, as well as the slope at any point. So say therefore, slope at point x is equal to 7 meters will become slope equal to, let's substitute 7, 47.54 times 7 square over 2 minus 20, 7 minus 4 minus 30 over 2, 7 minus 7 square minus 15, 7 minus 7 raised to power 3 over 6 plus 15, 7 minus 11.5 raised to power 3. When s is equal to 7, we give us, we work it out. Now, by Macaulay's principle, we know certain values are going to be cancelling out. So this is the expression for the slope. So when we substitute the value for s is equal to 7 into this expression for the slope, we're going to have it as this. Now, by Macaulay's principle, we know that all negative values are going, and we have this. This is okay. This one is going. So this is going. This is going already. We know by 0. This is going, and this is going. Okay. So what we're left with is, let's work on this. We are left with this expression, this one, and our constant. Okay. So let's work it out. So this is 851.17 as what we have. when x is equal to 7. So we can say that slope theta is equals to 851.17 over EI. Okay, so this becomes our slope at point S is equal to 7. Now the next question is calculating the deflection of this beam. Now for us to do the deflection, we will equate this expression to be 0. Okay, we can equate this expression to be 0. So if we do this, the maximum deflection will occur when this expression is 0. So we can say maximum deflection occurs where AI theta is equal to 0. Okay, so all we need to do is to equate this. So we do that, we are going to look for the value of x. So we'll say 47.54x to be 0. We look for the value of x, and we're going to come here and plug in that value where we solve that quadratic expression.
So when we solve that quadratic expression, we are going to have the value of x that will produce the maximum moment in this particular beam. Now, let's take note that the maximum moment, we can obtain it also when we have a uniformly distributed load. Note that the maximum moment is most likely to occur at the point where shear force is 0, because that is the turning point. So the turning point of your bending moment diagram indicates the point of maximum deflection. All right. Although it depends on the load configuration, but mostly for a beam of this nature that has some form of uniformly distributed load. All right. Thank you very much for watching, and do well to subscribe to our channel. I'll see you in our next class. Stay cool.